Hello, welcome back to three-phase circuits. We're talking about the summary of the voltage and current shifting rules in three-phase circuits. A lot of books will just throw this at you within the first 3 or 4 pages and say, solve a bunch of problems. And what we've done is a different approach. We've done the YY circuits, and now we're going to be working on the Y delta circuits where the load is now a delta. In the last section, we talked at length about the difference between phase voltage and so on, and we've done a lot of that work conceptually to pull it together for you. But now this lesson, I'm not going to write anything down. I'm just summarizing it for you, and it's going to be a short lesson. So here you have the same Y-connected load that we had previously, where we have a phase voltage, phase voltage labeled and a line voltage labeled. We also have the line current. And then over here, where you can see it and compare and contrast it, we have a delta connected load with similar things drawn. We have a line voltage drawn, we have a line current, and we have a phase current. We have the different loads drawn as well. So what we want to do is compare and contrast just to drill it into your head. Now let's go back to the Y circuit. Point number 1, the line voltage is not equal to the phase voltage for a Y-connected load. You know that. That means that this voltage is not the same as this voltage. Because they're not the same, we have to have a conversion rule. This is the one we've been using all through the last class. The line voltage is equal to square root of 3 times the phase voltage times this plus or minus 30 degree phase shift. We choose the top sign for positive phase sequence, the negative sign for the negative phase sequence. We've used this for dozens of problems before. Now in the delta load, we're going to look at the same thing. Line voltage is now equal to the phase voltage because the line voltage is here and it's directly connected across phase A, and you can prove it to yourself for the other phases, so the line voltage is equal to the phase voltage for a delta load. Because of that, we don't need a conversion equation because VAB, which is this, is equal to the phase voltage VAB. So they're actually the same thing, so we just write it as VAB equals VAB. You don't need to do anything. Okay, let's go back here and talk about currents. In the Y-connected load, the line current is equal to the phase current. That's because the line current comes in from the transmission line and it goes directly through the phase. So they're exactly the same. So because they're the same, you don't have any conversion relation between them, and you just note that the line current, AA, is equal to exactly this current going through the load. We call it AA, whatever. There's no conversion needed. But in the delta case, you can see right away that the line current is not equal to the phase current because the line current coming in, it splits off when it hits this node. Likewise, this line current is going to split here. This line current is going to split here. So they can't be equal. Because they're not equal, we require a conversion rule to solve our problems, and it takes the same form as the other one. We have the line current is equal to square root of 3 times the phase current. And we have a phase shift, but the phase shift is reversed. It's minus plus, where we choose the minus sign if it's a positive phase sequence, and we choose this bottom sign, which is plus, if it's a negative phase sequence. So that's the only real difference, but other than that, these equations are of the same form. So zoom back and make sure you understand this. This equation here, well, basically the bottom line, you should really think about this. You should have a mental image of these two pictures in your mind. That's why I keep drawing them. So you can remember what a Y load looks like, you remember what a delta load looks like. And you should know which quantities are the same in each case and which quantities are different. If the quantities are different, then they have to be converted using this equation, which is of the same form. It's a line quantity is equal to square root of 3 times a phase quantity times a phase shift. That's basically what it's going to be. And you can see that these guys here, if they're different, they require a conversion. In this case, the line voltage is different than the phase voltage, so we require a conversion equation to convert between them. In this case, the line current is different from the phase current, so we require an equation to shift between the currents, and this is what it is. In the other two cases, over here, in those cases, those quantities are the same, so we don't require any conversion between them. We don't have a magic conversion equation because we don't need it. So this is just a really short lesson to tabulate it all for you. Burn these equations in your mind, okay? You should already have this one in your mind from last time, but burn this one in your mind now, because what we're going to do in the next section, we're going to derive this equation so that you know where it comes from. It's not black magic, it's not hard, but you'll see where it comes from. But ultimately, most of this class is going to be using this equation to solve delta load problems, right? And so we'll get there. And you can get into weird cases where you have a delta load up here, and then in parallel with that delta load, you have a Y load. So you can actually have a delta load and then in parallel with it a Y load. So you might need this equation for the Y part of the circuit. You might need this equation for the delta part of the circuit. And we'll get there when we get there, but that's the roadmap. These are the two magic equations that we're going to use. Follow me on to the next section. We'll derive this equation and then crank through some problems to get you real practice.